All right, guys, welcome to FRE's first guest lecture of 2020. Today, we're going to have CJ talk about diagonalization, and, well, I'll let CJ take it away. You should unmute your mic, CJ. Unmute your mic.
CJ says his laptop just crashed.
Okay. Well, guys, just wait for a little bit, and we'll see if we can get CJ back.
Yeah. How's the first week going for everyone? Yes, there is going to be a recording of this. Well, I guess nobody likes how the first week has been going. Thank you, Poonam. I appreciate that. Going where? Yeah, the last few days of each week is going to be difficult, and that's okay because it's hard to really learn stuff if you're not doing difficult things. We'll send the recording to you. We will do that, right? Someone confirm this.
Yeah, this meeting is being recorded.
Yes, it is Andrew Wu speaking right now. Thumbs up. Thank you. CJ says about 3 minutes until his laptop gets unkilled. So yeah, 3 minutes left. You know, you guys should unmute and talk if you want. Like, there's nothing wrong with that.
Oops, sorry. My laptop is currently dead, but I'm currently on my phone, so I can talk for like 3 minutes and give an intro until my laptop is ready. Does that sound good?
That sounds great. Go ahead.
All right. So today we're going to talk about diagonalization. So many of you may have heard about Gödel's first incompleteness theorem, which is like this really hyped up thing that says that, a logical system can't be both complete and sound. And what these two words mean, complete and sound, a logical system is complete if it either proves or disproves every single statement that you can make in the system. And a logical system is sound, or I mean something stronger than soundness is consistent. A logical system is consistent if you can't prove both something and the negation of that thing. So Gödel's incompleteness theorem says that you can't have both. Either your system is consistent and there are going to be statements that you cannot prove or disprove, or your system is complete, but it's inconsistent. There are statements that you both can prove and disprove, which is like a problem. Yeah. So, all right. So So that's usually where like the discourse about Gödel's incompleteness theorem ends. And sometimes if you like see a proof of Gödel's incompleteness theorem, it usually goes something like this. There's a statement called the Gödel sentence, which says, okay, let's say that you have a formal system. This is kind of hard to explain without drawing things, so you're going to have to bear with me. Let's say that this formal system's name is something like Leonard. And Leonard claims that he is both sound and he's both consistent and complete. And so you ask Leonard to prove the statement. The statement is, Leonard cannot prove this statement. So let's think about the possibilities, right? Suppose that Leonard does prove the statement, which means that the statement is true, and Leonard cannot prove the statement, which is like a contradiction, because you just proved that you can't prove it, which is like impossible. So it's inconsistent. Similarly, if you disprove the statement, that means that you can't prove it, which means that the statement would be true, which is, another inconsistency. So if Leonard is able to prove this statement, that means that Leonard is inconsistent. So the only option is for Leonard to be incomplete. Consistent and sound. Okay, I'm not going to talk about soundness in this talk. I'm just going to use consistence for simplicity. Consistent means that you can't prove a statement and its negation. Or in other words, it's just like the system makes sense, basically. Does that answer the question? All right. So yeah, either Leonard proves or disproves the statement, which means that Leonard is inconsistent, or Leonard shuts up and he doesn't say anything, which means that he can't prove the statement or disprove it, which means that Leonard is incomplete. And the goal of like Gödel's the goal. So usually the presentation ends there, and it doesn't actually go into like a formal proof of Gödel's first incompleteness theorem, because it turns out that the formal proof is actually like quite complicated. In order to like encode what it means for something to be able to be proved, it actually is like you have to convert it into numbers in the system called Gödel numbering, and it's like kind of complicated and pretty bad, which is why like entire chapters of books are dedicated to this. And if you're interested in the classical proof, I guess you can read that up on your own time. But today we're going to talk about a proof of Gödel's, entire books. Today we're going to talk about a proof of Gödel's first incompleteness theorem that doesn't require any of that. All right, this is about the end of the part of the intro where I can move without having to draw things. So, oops, and my laptop still isn't ready, unfortunately. Okay, I'm gonna start going more slowly, and hopefully my laptop will start in the next 2 or 3 minutes. All right. So what does it mean to be able to prove or disprove something? What is the system that we are working with? It turns out that most of modern mathematics is built on something called CFC, which are the Zermelo-Fraenkel axioms plus choice. Basically, every single statement that we do in math, every single textbook, every single paper, every single result that has been made in like the past 2, 3, 4 decades or so, almost all of these results rely on CFC, or like assume that CFC is true, and then just like prove things using CFC. It's surprising how basically everything comes from CFC when CFC is as simple as like 9 axioms, and the first 6 axioms are kind of boring, and they basically just say, oh, this is a set, you can make a smaller set out of it. Yeah. Okay, I will explain what CFC is once I get... Holy shit, okay, my laptop's on. All right. Let me join the call from my laptop. All right, am I not muted now? I'll assume that I'm not muted.
You're all good, CJ.
Wonderful. Great. Finally, we can continue. All right. Let's talk about ZFC. So ZFC is a set of rules. Um, and these rules are basically like axioms. And the axioms tell us what we can do with math. Basically, what ZFC does is that it turns the entire universe into sets. So everything is sets. The only thing that exists are sets. Everything is sets, sets of sets, sets of sets of sets, and so on. And ZFC's 9 axioms tell us what we can do with sets. So for example, the first 6 axioms tell us how we can make smaller sets from sets. So you can take a set, and then you can give a smaller set. Or like, you can take 2 sets, and then you can combine them into a single set, and stuff like that. So none of these are like huge sets, right? Like these are all sets that are like very small, very reasonable to assume exist. Um, oh, by the way, I can't see the chat now that I'm sharing my screen. So if anyone has questions in the chat, someone will have to read them out to me. Feel free to interrupt me at any moment, I guess. Okay, so I talked about the first 6 axioms, and they tell us that we can take sets and make smaller sets. The 9th axiom is choice. Choice is pretty complicated. I'm not going to talk about it right now. It's the 7th and the 8th axioms that are interesting. The 7th axiom asserts the existence of n, the natural numbers. The natural numbers are, 0, 1, 2, and so on. And basically what the 7th axiom says is that n exists. And then there's the 8th axiom. The 8th axiom is power set. Power set takes a set S and gives you the power set, which is like the set of all subsets of S. So for example, if you take the set like 0, 1, then the power set would be the set that has the null set, the set that has 0, 1, and the set itself. All right. So it's interesting that the 9 different axioms, basically these 6 are like tiny axioms. The 7 and 8 are like the only truly big axioms. They're what make ZFC ZFC. And the reason for that being is that if you assume if ZFC is true, inside ZFC there are lots of sets. So like for example, there's n, which is from axiom 7. And then there are subsets of n, which we know exists. Like say there's like 0. There's like 0 or 1, or the set like 0, 1, 2. These are all sets that exist because they're all subsets of n. And then there are like the power, and then there's also the power set of n, which is 2 to the n. And then there's also the power set of that, which is 2 to the 2 to the n. And then there's also the power set of the power set of the power set of that. And this is like, like you get like more and more and more and more and more sets. And this is like a lot of sets. Like you're asking for like all of these sets should exist in ZFC. And so there are a lot, right? And I guess one of the question is, can you do math with less sets? And it turns out that the answer is yes. Um, so before we talk about that, I guess the one reason that I wanted to say about this is there are why do we care about this? Why do we care that this gap is so big? Why do we care that this exists or not exists? It's because 2 to the n is way larger than n. So let's say that 2 to the n wasn't as large, right? Let's say that there was like some way to list down all of the elements of 2 to the n. So let's say that this first element is just the set of all even numbers, And recall to the n is like the set of all subsets of n. So its elements are just subsets of n. So let's say this first one is like the set of all even numbers. This next one is like the set of all primes. And then this next set is like the empty set. And then this next set is just the set consisting of 1 and 2, and so on. And let's say that, there are only n of these. Or what it mean, I mean, you can like comparing infinities is kind of hard. So the way that we usually do it is that we like biject them instead. Which means that, there's 0, 1, 2, 3, and so on. And what you do is that you assign this set the number 0, this set the number 1, this set the number 2, this is 3, and so on. So here's the problem. We can make a table that looks like this: 0, 1, 2, 3, and so on. And then we can fill it out with 1 if we can fill out the entry with 1 if this number is in this set, and 0 otherwise. So for example, this number would be 0 because 0 is not in the set. This is also 0. This is 1. This is 0, and so on. And then you can fill out the rest of these numbers like so. I changed my mind. I want to change the set. Let's make this set set of all natural numbers, which is, also a set. Okay. And this would all be all ones. And, you would keep filling this. Sorry. It looks like my laptop is not liking me again. Wow. Don't we just love technical difficulties? All right. Cool. Oh, yay. I got it to work. Haha. Okay. So let's say that we did list all of these numbers like this. And then what we're going to do is we're going to take the opposite of this. So the opposite of 0 would be 1. And then the opposite of this 0 would be 1. And we're going to take everything along the diagonal, and we're just going to take like the negation, right? And these numbers themselves, they describe a set. This is the set that has 1, 2, 3. No, wait, no, not 1, 2, 3. It has 0, 1, 2. It doesn't have 3, and so on. Um, so the question is this one of the sets in this list? Like, does this correspond to a number n? And the answer is that it can't, because if it does, then does this set contain n or not? If you continue this along the diagonal, right? Recall that the way we define the set in the first place is such that this number is the opposite of this number. So that means that the number, whatever number we're going to put here, this number has to be the opposite of itself. So if it's 0, it had to be 1, and if it's 1, it had to be 0, which can't happen, right? So that means that this set does not exist in this list. So that means that there are sets in 2 to the n which can't be bijected in n. So that means that this bijection doesn't exist in the first place. And I guess, this is like the classic diagonalization proof that we often talk about. So maybe you've heard of like Cantor diagonalization, and this is precisely that idea. You can use the same idea to show that there are more real numbers than natural numbers, whatever that means. And this is the problem that I talked about earlier. This is a genuinely big step because 2 to the n is like way huge compared to n. It's like so large that we can't even list all of the sets down infinitely. It's like that big. And this one, using the same idea, this one has to be even bigger than this, and so on. And not only does ZFC contain this or this or this, it contains all of this stretched out to infinity, which is huge. There's so many sets. And this is why I was like, it's kind of hard to believe that this many sets exist. So maybe let's start with something simpler. And there's a simpler system of axioms, which are called piano arithmetic. And I'm going to describe them now. But before we get to that, are there any questions? I actually don't know how it's pronounced. Is it piano? Pino? I don't know. Anyway, I like piano, so I'm gonna say piano. All right. It doesn't seem that there are any questions, so I'm gonna keep going. All right. So the piano in CFC. Oh, yeah. There's a question. Yeah.
We have a question. Alex is asking, aren't all the sets in 2 to the 2 to the n in 2 to the n?
That's a good question. Aren't all the sets in 2 to the 2 to the n in 2 to the 2 to the n? Okay, sure. Aren't all the sets in 2 to the n in n? Because like it's the same idea, right? So all right. How do I explain this? So in n, oh, okay, in n, the things that exist in n are like 0, 1, 3, 42, and that kind of thing. In 2 to the n, the things that exist are the set of 0 and 1, the set with 3 and 4, and so on. In 2 to the 2 to the n, the things that exist are sets of sets. So 0 and 1, 3, 4. Like you could have a set that looks like this, and so on. And this one is even larger. And like these are just the elements. And CFC contains all of these sets. Does that answer the question? All right. Let's keep going. So can we do math with less sets? And it turns out that the piano axioms only assume significantly less sets. In the piano axioms, the only thing that exists is 0 for now. That's what the first axiom of the piano axiom says, that 0 exists. Right. And then there's actually 9 axioms in the piano axioms. Piano, I don't know. Okay, there are 9 axioms in the piano axioms. The first one says that 0 exists. 2 through 5 define the equal sign. 6 through 8 define S. And S is just like a special function that like takes a number to the number after it. It's short for successor. So S0 is 1, SS0 is 2, SSS0 is 3, and so on. So all of these axioms so far are pretty boring. And it's the 9th axiom that's interesting. This axiom is induction. And the induction axiom says, so it takes a bit of work to define it, but I'm going to try. If, let's say, okay, if P of 0 is true, and if P of n implies P of n plus 1, then P of n is true for all n in n. Okay, so P here is a property, right? Like a property could be something like so yeah, that's exactly the question. What is a property? What do we mean by a property? When we do induction, usually these properties are statements like, oh, this statement is true for n equals 0, and it's true for n equals 1, and it's true for and so on. But like, what does a statement mean? That's like extremely vague. Like all of these are such formal definitions, and yet induction is this one sketchy definition that has this is property, but we're not going to tell you what property is. So that's because there are actually 2 kinds of piano arithmetic, which I'm going to call, there's like piano arithmetic second order, and there's piano arithmetic first order. And in piano arithmetic first order, a property is just like any set, or like any subset of n. So you say that P of n holds if n is inside this set. And like, PA2 isn't that much better than ZFC, because in PA2, statement 9 is a statement over all sets, or like all sets of natural numbers, which is no better, because that means that to state this 9th statement, you have to assume 2 to the n exists in the first place, and this was the problem that we were trying to avoid. We're trying to like not refer to 2 to the n, so we don't want to do PA2. PA2 is too big. Instead, what we're going to define as a property, and here we're going to use the PA1 version, which is like the typical version of PA. A property is something that's satisfied by a formula. And the formula is just something that takes a number in n, and then it evaluates to either true or false. Like for example, you could have a formula is even. You could have a formula called is even, which is true. This formula takes in a single number n, and it's true if n is even, and it's false if n is not even. So, okay, I guess I replaced one vague thing formula with another. I replaced one vague thing property with another vague thing formula. But now formula actually has a formal definition. A formula consists of these symbols. It consists of numbers in n. So it can contain like 0, 1, 42, and so on. It consists of variables. We assume there are infinitely many variables, A, B, C, N, and so on. And then it consists of like only these things. It consists of addition, multiplication, less than, greater than, equal to, left paren, right paren, and, which is the logical and, or not, for all, and there exists. So that's it. That's the only things that are contained in a formula. And you might wonder, don't formulas sound very weak? Well, turns out that like, almost all math can be written in formulas. Okay, that's a pretty important statement, so I'm going to write that down properly. Almost all math can be a PA formula. And by almost all, we mean like pretty much all the math that you will encounter, unless you're a set theorist or like an infinite combinatorialist. This includes, all of your high school algebra, all of arithmetic, all of Euclidean geometry is encapsulated in PA formulas. Most of elementary number theory, most of calculus is like also in PA formulas. Analysis, most of topology, as long as you don't go into like very infinite topology. Combinatorics, as long as you're not dealing with like very, very big things. All of these things, they're all in PA. And it's kind of hard to believe that, using just this extremely limited set of symbols, you can express all of these ideas. But I'm going to give an example that will help you convince that we can write everything in formulas. All right. The formula that I'm going to write is something that expresses that there are an infinite amount of primes, or that there are an infinite number of primes. Okay. So we're going to start by defining divides. Okay. We say that a number d divides a number n if for all k. Wait, no, not for all. I don't want to do that. I want to say there exists some e less than n such that d times e is equal to n. Right. So basically, this is a formula that takes in two numbers, and then it outputs either true or false. It's true if there does exist, and it's false if there doesn't exist. So for example, 2, 6. Is divides true for 2, 6? Well, it is, because there's a number 3. And 3 is less than 6, and 2 times 3 is equal to 6. So this is true. All right. So now that we've written divides, let's move one step forward and write is prime. So this will be a formula that takes in a single number n and tells us whether n is prime. So this says that for all, let's say k less than n, either k is equal to 1 or not divides. Okay, I'm running out of space. I didn't plan this that well. Not divides kn. Wow, okay, I fit it. I'm so good. All right. So either so for all k less than n, either k equals 1 or not divides kn. Does this formula make sense to people? Do you see why this is like a good definition of why it's a prime? Because let's say like this is a number like 5, right? So for all k less than n, where k is like implicitly a natural number, so we check. Okay, I guess you also have to say. Oh, I mean 0. I guess you also have to say that. Actually, no. Yeah, sure. Um, Sorry about that. So let's say 0. Um, 0 is not 1, so that's not satisfied. But does 0 divide 5? Well, is there a number e such that 0 times e equals 5? There isn't. Okay. So, oh yeah. So because there isn't, then not has to be true. So that means that it's satisfied for 0. And then similarly, you can check it's 1 because k equals 1 satisfies it. 2 is also satisfied because 2 does not divide 5. And similarly for 3 and 4. So because this is true for all numbers less than 5, is prime 5 is true. And that gives us like, the definition of is prime. Okay. I hope that makes sense. Next, we're going to define has larger prime. Has larger prime n. This is like a pretty simple formula. Um, this formula is just true if there exists some prime number p such that p is greater than n and is prime p. So, it just basically says that there's a larger prime than n. And finally, the statement that there are infinite primes is just now for all n has larger prime n. So n has a larger prime, which means that for all numbers n, I can name a prime that is larger than n. And so now we've written the statement that there are infinitely many primes using just these simple things, using just the only things that we use were numbers. We use 1, we use some variables, we use multiplication, we use less than and greater than and equals and parentheses and or not for else. For all and equals, for all and there exists. And that's like the only thing we use in our formula, and we were able to talk about infinite primes. And similarly, um, there are like a lot of other things that you can write with formulas as well. I'm running out of space, so maybe I should continue in the next slide. So, um, okay. So notice that we define the formula is prime, and the only so okay, let me collect my thoughts for a moment. Sorry. Right. So the only sets in PA are n and subsets of n that are described by a formula. So which sets does this include? Well, for example, it includes the set of all prime numbers because we literally just wrote the formula for is prime. It includes things like, a set that's just like finite, like a 142, because the formula for this is like n equals 1 or n equals 42. So this is just the set of all n such that n equals 1 or n equals 42. It includes sets like, say, all n such that there exists x, y, z, such that x cubed plus y cubed plus z cubed equals n. And you can already like pretty much see how to convert this in the formula that we expressed earlier. It's like pretty close. It also includes n such that there exists x, y, z, such that x to the n plus y to the n is equal to z to the n. Or like all natural numbers for which there's an example for x to the n plus y to the n equals z to the n. And now that we know that Fermat's last theorem is true, we happen to know what the set is. But even if you didn't know what that set is, you can just like, you can write it down as a formula. Exponentiation is kind of hard, but you can write it down. And it includes things like, all n such that the nth digit of pi the nth digit of pi is 7 for like however you want to define digit. And like this is harder to write, but it is possible. And you know, there are like so many things that we can write. Like I said, um, all of these, there's so many different sets that we can write, and all of these sets, pretty much cover most of the math that you'll ever use in your everyday life, and even in your not everyday life. But the question is PA really smaller? Is it really smaller than ZFC? Um, is it true that the subsets of n that have a formula is actually not just all of the subsets of n? And the answer is, I mean, yes. And there are two ways to see this. So I'm going to talk about the first way. The first way is that um, recall that when we said a formula, I mean, I've written that down earlier, so maybe I can just copy that. Okay, a formula consists of, let me copy this, uh, and let me go back to that page. All right. Okay, so a formula consists of numbers, variables, addition, multiplication, less than, greater than, equal, parentheses, and or not for all there exists. Um, there are infinitely many numbers, but in fact, we can just like write them using only 0 and s, because there's just 0, which is 0, s0, which is 1, ss0, which is 2, and so on. Um, and similarly, there may be infinitely many variables, but we can express those using just like say n and like a prime, and then you can just name your variables n prime, n prime prime, and so on. And so that means that you only have a limited alphabet. Your alphabet, your alphabet for constructing formulas only consists of these. It only consists of 0, s, n, prime, plus, times, less than, greater than, equals, left paren, right paren, and or not for all there exists. There are only 16 letters in our alphabet, which means that you can write down, let's say, all of the length 1 formulas like in dictionary order, right? So let's say that we take all valid length 1 formulas, like 0, s, and so on. Well, many of these aren't valid, like s isn't valid because it needs to be after 0. But like we can just drop all the ones that aren't valid. And then you can include the length 2 formulas, like say 0s, which is not valid, like 0n, 0 prime. Many of these aren't valid, but it doesn't matter. And then you can include the length 3, 0, 0, 0. It'll include things like plus times less than. It will include things like plus n, right paren. But like the point is, however way you list it, there is a bijection. We can assign a natural number to each one. We can say this one is 0, this one is formula 1, this one is formula 2, this one is formula 42, 43, and so on. And so the formulas are in bijection with n. And we know that n is not in bijection with the power set of n. So that means that there are definitely subsets that we can't describe with a formula. So surely, if a set can't be described with a formula, it must be really, really ugly, right? Like we said earlier, there are so many things that we can describe with formulas. Um, like we can say we can describe all of these with formulas, but do we have like a very specific example of what? Mm, okay, I can give like let's see. Someone brought up to me that there was a question about and being unnecessary because we have or and not. Yeah, that's a really good point. I think the thing that matters in the end is that you just have a finite alphabet. All right, but yeah, that's a really really good observation. Cool. Where was I? I was talking about formulas. All right. So here's another way to show that there are subsets of n we can't express with formulas other than just a counting argument. So let's say that we listed down all of our formulas using the technique we did earlier, which is like, the technique where we um, like take all of the length 1, length 2, and take only the valid ones. And let's say that all of these formulas, all of these formulas take in a single integer, and they evaluate to either true or false. So, all right. And now let's take all of these formulas and let's evaluate them on 0, 1, 2, 3, 4, and so on, right? So let's say that this one is true on like all numbers. Let's say this one is like true only if it's an even number. Let's say that this one is like false for this one is prime. This one is our is prime formula. Let's say that this one is just like always false, and so on. And you can like list all of the formulas and all of the numbers and that kind of stuff. And we know that this list exists, right? We know this list exists because we just showed that it exists. So each of these is a subset. This is the subset 0, 1, 2, and so on. This is the subset 0, 2, 4, and so on. And this is subset 2, 3, 5. All right. Now we're going to construct a subset of 2 to the n that does not exist in this list, that is not described by a formula. And what we're going to do is we're going to take this, everything in the diagonal, once again, we're going to use the same trick, and then we're going to take its opposite. And this is going to be the set, it has 1, 3, and so on. If you were to write this as a quote unquote formula, if you use things that are like not in our system, it would be, this formula would be not f of n, where we call this formula g of n. And the question is, does g appear in this list? And if it did appear in the list, let's say that g is equal to f of k. So the question is, what is f of k of k? Because of the way that it's defined, if this was, again, you get f of k has to be equal to not f of k, which is a contradiction. In other words, what's happening here is the same thing that's happening earlier. This number is the opposite of this number. This is the opposite of this. This is the opposite of this. This is the opposite of this, and so on. And then when you intersect these, there's nothing that can go in this spot. This can't be true. This can't be false. Therefore, this does not exist in the list. Yeah. All right. So this was like essentially the same idea, right? This is like the same idea that we used earlier, except now we're using it in a completely different context. Now we're showing that there are formulas, there are like ways to describe sets that can't be written down with formulas in PA. All right. So what do all of this have to do with Gödel's first incompleteness theorem? I promised that we were going to get to a proof of incompleteness. And the reason that I brought all of this up is so that we can, give the necessary background for understanding the proof. We're going to get very meta really soon. So I think it's important to pay a bit more attention, and please ask questions if anything gets confusing, because we're going to become really, really confusing really soon. Kind of, I guess. I hope not, but All right. So rather than talking about incompleteness directly, rather than like showing that PA is in itself incomplete, this is like kind of like a similar idea, right? This is like kind of like an incomplete thing in PA. There's like a set that we just wrote down, but it's not in PA. We can describe the set, but we can't write it down using a formula. And this is like kind of like a similar thing that's happening here in spirit. So what we're going to do, maybe you've heard of something called the halting problem. Um, and I'm going to introduce something called the guessing problem, which is kind of similar. So this requires the idea of a Turing machine. And a Turing machine is basically, for our purposes, a Turing machine we can think of as just like a function. A Turing machine is a function that takes in an input, and it either accepts the input or rejects the input, or it runs forever. And so if you've heard of the halting problem asks, is there a program that given a program as input determines whether it halts forever, whether it runs forever, or whether it eventually stops? And this is like the same thing as the guessing problem. Is there a program that takes in some program, let's call it P, and if px, okay, let's call this program M, or it's a guesser, so let's call it G. So is there a program? It takes in an input. The input is another program. So is there a program G such that if P is run on P, and this is, if this accepts, then G accepts. If P of P rejects, then G rejects. And if P of P runs forever, well, this is the tricky part. Instead of running forever, we want G to just, either accept or reject, but it doesn't really matter as long as it actually stops rather than runs forever. So this is kind of like the halting problem. It's a bit more specific, but yeah. So basically, is there a program G that does these things? And the answer is that there isn't. And the proof of this goes something like this. So let's say that we did have this program G. Using G, we can construct another program, which we're going to call G prime. And G prime takes a program P, and if P of P accepts, then G prime rejects. If P of P rejects, then G prime accepts. And if P of P runs forever, then G prime either accepts or rejects. It doesn't really matter. And the big question is, what happens if you run G prime on G prime? So let's take this and let's write G prime in our definition. Okay. So if G of G prime is an accept, then actually G of G prime is a rejection. If G prime of G prime is a rejection, then actually it's an accept. So this is impossible, and this is impossible. But if G prime of G prime runs forever, then it's going to halt either way, which contradicts the fact that it runs forever. So it doesn't, yeah. So G prime can't exist, right? Like we already showed that none of these values work for G prime. So therefore, because G prime doesn't exist, G can't exist either. So we can't solve the consistent guessing problem. How is this related to anything we talked about earlier? Well, this is like the same idea we saw earlier, right? Of like putting something into itself. And this is like the spirit of diagonalization. And if you really wanted to draw the diagonals for this, the way it would look like is if you had like a list of programs here on the bottom, here on the side, and then you had like the same list of programs here. And then you get like, say, this P1 run on P1 accepts or rejects or runs forever, or rejects, 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 or forever, 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 or accepts, 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 and so on. And then you're saying that G prime is one of these programs, except that it's the opposite of everything on the diagonal. So it's going to be reject here, it's going to be accept here, it's going to be something here, whether it's reject or accept. And then again, the problem happens if what happens when you run G prime on G prime, it can't be accept, it can't be reject, and it can't run forever, so it can't exist. This is like the same spirit of diagonalization, except that, when people present this proof, they never say that it's diagonalization, which I think kind of obscures the point. Like spiritually, this is still an example of diagonalization, and I think that's what makes it like easier to understand, I guess. All right, that was pretty meta. Were there any questions about that so far? Okay. I don't hear anything, so I'm gonna keep going. All right. So let's say, oh
See,
yeah.
Someone is asking, what is P of P?
What is P of P? So P, recall that P is a program. P is a program that takes in an input and it outputs either accept, reject, or runs forever. So P of P is just like P. You take the program P and you put it as input into itself. Does that make sense? Like, um, for example, if you had a program where that printed its input, then if you print the input of the source code, that would be the result of running P on itself. Like you take the source code of P, which is like a string, and then you can put it as input into a P, where P is like a program that takes in a string. Does that make sense? All right. Okay. Finally, we can get to the point of this talk. What does all of this have to do with incompleteness? Let's go back to our example of Leonard. So let's say that Leonard is both complete and consistent. So that means that Leonard can either prove or disprove everything. And consistent means that, it's just consistent. Like it can't prove A and not A. It can't prove both something and its negation. That's what it means for it to be consistent. All right. What we're going to ask Leonard to do is we're going to consider the statement. Let's say that P is a program, right? Or like any kind of program. And we're going to consider the statement P of P accepts. And we're going to ask Leonard to list down all of the proofs of this. So let's say Leonard is something like, if Leonard was something like Z of C or like PA, you can imagine Leonard just like listing down all of the length 1 proofs or length 2 proofs or length 3 proofs and so on. And like you basically look at like the list of proofs and you check if this proof is a proof of this statement. All right. Now let's think about what happens. Suppose that Leonard finds a proof that P of P accepts. And like Leonard always finds a proof. Leonard always finds a proof or disproof. Well, that would mean that he's inconsistent. Why? Because we already showed earlier that there isn't a program that solves this guessing problem, right? There isn't some kind of program that can solve the problem of this or like always determine whether it accepts or rejects or, finds a disproof of it. So if Leonard could always prove this, that means that he can solve this problem. And
See,
yeah.
A student wants to know, what is Leonard again?
Oh yeah, Leonard is an axiom system. Leonard is something like ZFC or PA, or like basically Leonard is something that can generate proofs. And we're trying to show that Leonard cannot generate proofs of statements that are true. Or like we're trying to show that Leonard is not complete or cannot be both complete and inconsistent. All right. So if Leonard always proves or disproves this statement, then that means he has to be inconsistent. We know that there is no way that this statement can always be proved or disproved because that would solve the consistent guessing problem. And we know that a consistent system can't solve the consistent guessing problem. So this is impossible. So that means that there has to be some kinds of programs for some P. Leonard neither proves nor disproves. Leonard neither proves nor disproves this statement. And that means that Leonard has to be incomplete. That means that there have to be statements that Leonard can neither show are true or false. And we gave an explicit example of a statement, just like this P, Leonard can't prove that it either accepts or rejects. So yeah, that's basically the proof of Gödel's incompleteness theorem. Notice the difference between this and the sketch that we provided earlier, in that we have this much nicer sentence where Leonard talks about programs instead of our original sentence where Leonard talks about this statement can't be proved. Like making a statement refer to itself is like pretty hard to write up in formulas and like formally, but we were able to write up something of a similar kind by referring to something outside Leonard, which are Turing machines, which are like nice. Anyway, yeah, this is like the proof of Gödel's first incompleteness theorem. If Leonard is powerful enough to talk about Turing machines, then Leonard is either inconsistent or incomplete or both. Yeah. And that's it. I think that's it for the talk. Are there any questions about any of that? I know it was pretty long and it got pretty meta at times. But yeah, that's it.
I would ask for a proper round of applause, but people don't seem keen on unmuting. Although if you do see the CJ, can you see the chat right now or no?
I cannot see the chat right now. Should I try to like stop sharing and then see the chat?
Someone is asking, are you referring to Turing machines?
Yes, I was referring to Turing machines. It turns out that the nice way to prove this is to not just refer to the system of Leonard himself, but it actually becomes easier if instead of just accepting Leonard, you also like make Leonard powerful enough to talk about Turing machines. And like, for example, piano arithmetic is powerful enough to talk about Turing machines. So therefore, piano arithmetic has to be either incomplete or inconsistent.
Someone else is asking, how can this be applied in astrophysics?
I have no idea how it can be applied to astrophysics. I'm sorry. I don't do astrophysics. I don't do any physics at all.
Someone else is asking, does that mean that some problems like the Millennium Problems cannot be solved?
Yeah, that's a very good question. Well, it actually turns out that so there was this problem called the Continuum Hypothesis, which is pretty famous for some time, and can't be solved. So we actually showed that it's the Continuum Hypothesis is something that you can't prove or disprove in ZFC. And I guess knowing that you can't prove or disprove it is a solution in itself, I guess, because you have to prove that you can't prove or disprove it. Does that make sense? So it might turn out, for example, that the Riemann hypothesis is neither true nor false. It's just that ZFC or like our system of math is not constrained enough to determine whether it is true or false. And that can be one way to solve the Riemann hypothesis. I mean, I think it's true, but like, that's one possibility. So by self-consistent, um, in other words, it means that there are always things that we can't prove, no matter what we make our axioms. And sometimes we just have to be happy that we can't prove some things. And if you try to make yourself able to prove everything, if you try to make a system complete, then it has to be inconsistent. That means that if you try to prove everything, you're going to like say some things that are wrong, which means that we just have to satisfy ourselves with like not being able to prove or disprove everything. So yeah, that is what Gödel's incompleteness theorem says. Maybe you might be familiar with Gödel's second incompleteness theorem, which says that something can't prove that itself is consistent. There's in fact like a similar proof of this, but it's like more complicated, and I don't really have enough time to talk about it. But yeah, I don't know. I think logic is interesting, and it's not something that people talk about a lot. So
CJ,
yeah.
would you be willing to answer like general questions too, like not necessarily related to your topic?
Oh, definitely. I'm free to answer like questions not necessarily related to my talk.
CJ is really, really cool. Like, he's an incredible person who has some incredible stories to tell, so you guys can ask him anything. Poonam Sahu asks, what is your favorite triangle center?
Mine is the in-center because it does not lie on the Euler line, so it's special.
Jet Chung asks, what's MIT like?
MIT is a lot of things to a lot of people. For me, MIT was a place where I got to find a group of people, a group of friends whom I like really connected with for like a long period of time. And even though I found this community of people in like math camps or something, being in MIT means being around these kinds of people that I like being around all the time. And I think that's one of the most valuable parts of being in college. What did I have for breakfast? I got bacon. Which of EI Pi 01 do you like the best? 0. Milk or cereal first? Um, Fight me for this, but I am a milk first person. Can you give me a hug? Unfortunately, I am not able to give you a hug right now, but I would, with your consent. What is your favorite math problem? That's hard. I haven't actually talked about that. So I'm just going to not answer that question. Can we call you Josh? Please do not. Favorite proof of a math theorem? I don't know. I have lots of proofs. Definitely this proof of Gödel's first incompleteness is like probably in the top 10 or so, just because it's like not one of the class, just because it's like so much nicer compared to the classic proof. And it's also kind of surprising that it works. What's your favorite competition math problem? Um, so my favorite competition math problem is actually one of the problems that haven't. Here, I guess I can just describe my favorite competition math problem. Um, Let me share my screen again. My favorite competition math problem goes something like this. Let me pull up a whiteboard. So you have this quadrilateral like this, and there are these points trisect this side, and these points trisect that side. Well, maybe it's not my favorite of all time, but it's definitely in like my top 10 or something. We tell you the length of this, which is like, let's say for concreteness, this is like 16, this is like 25, this is like 18. What is this length? Yeah, that's my favorite problem. Well, one of my favorites, I guess. Probably not my most favorite. Uh, Favorite number of the alphabet? I don't think the alphabet has numbers. Favorite question I've been asked? Probably has to be cereal or milk. That was a pretty good question. Favorite theorem? I don't have a favorite theorem. I know, it's heretical. How to excel in Olympiad problems? Practice, I guess. There's not really much to talk about other than like what has been. I think Evan Chen wrote an article about, called like math contest platitudes. And if I were to answer how to excel in Olympiad problems right now, I would be basically repeating that article. And it's a really good article, so I just recommend that you read it. What branch of math do you specialize in? Um, I don't know. I'm a first year. I haven't specialized yet. Road to IOI. Is that what that question is? Road to IOI? Oh, be born in a country where not a lot of people are competing for the IOI, I guess. How do you prevent hair loss? If you figure out, let me know. I've been having a higher rate these past few days. PC or console? PC. I've never touched the console in the past 3 years. Whether I've conducted any specialized research already. I mean, I've co-written like 3 papers on graph theory, which I guess it would look like I specialize in, but I don't know. I find a lot of things interesting other than graph theory. Ross or promise? Definitely promise. Yeah, I don't know. I hope that you guys at least understood some part of the talk. Like this is like the kind of topic that I wish someone explained to me well, but no one ever did, which is sad. How do you write problems? I don't know. It's kind of like spontaneous-ish sometimes. Sometimes I have a really good idea for a mechanism for a problem and I just write in front of that. Sometimes I specifically try to write a problem where like, oh, I want to write a problem about polynomials and rational numbers and stuff. And then I just like try to write a specific problem like that. So how to do combo? I don't know. How do you pronounce your last name again? Quines, not Quines. Although I do like Quines. Quines. Our topic was actually kind of related to Quines, in a way that I do not want to talk about because it would take too long. I guess that's pretty much it. Is there anything else that we're waiting for? What's the most important thing you think you could tell a high schooler today? I think I want to say something like, don't waste your time or something. In the sense that, not that like you shouldn't like spend time playing video games or hanging out with friends or anything, but in the sense of like when you do things, you should have like a very good idea of like why you're doing it. Like for a long time, competition math for me was just something that I did without thinking about why I was doing it. And I don't know, I was pretty unhappy about it for a long time. When I finally realized that the thing that I liked most about competition math wasn't like solving problems really quickly, but it was actually hanging out with the people. And so I told myself I wanted to be good at comp math so that I can hang out with these people more. And I think that was like fun. And I think thinking about like, what you're doing, not just like, I mean, it's really easy to just like, oh, I'm going to like practice because I want to make X or I want to make Y next year. But like thinking about even deeper than that, but like, does this actually make me happy? This is something that I actually like. And I recognize that not everyone has like, the privilege to be able to think about this. I'm lucky that my parents weren't like people who forced on me to like do things that much. But even if they did, I think I just really valued the time that I spent thinking about the things that I was doing. And what I mean by don't waste your time is don't do things you don't know why you're doing. Because in the end, even if you change your mind about why you're doing it, at least you're going to say you did it for a reason. That was very philosophical. Someone asked a silly question. What's the best instrument? Um, I really like, I really like the piano, but I'm going to say the theremin. I don't play the theremin, but the theremin is pretty cool. Pew or Rudin? I haven't read either book. I am so sorry. I'm such a bad person. Analysis or algebra? Algebra hands down. Are we just going? Am I just going to keep answering silly questions?
I think it's probably time we release you from your duties. Thank you so
Cool.
much for this talk. I can only speak for myself, but I hope everyone enjoyed it a lot and got a lot from it. Yeah, I really enjoyed it. I hope everyone else enjoyed it, and we're really
Yeah.
grateful that you.
If you guys, I wanted to say that if you guys have like any remaining questions, my inbox is open. So just like feel free to contact me if you have questions about math or silly questions. And I definitely try to respond to all of my emails. And I'm pretty good about that as long as it doesn't fall into my spam. So yeah.
CJ, is there anything you want to plug before you leave, like your website or your articles?
No. Thank you
sure?
for plugging it for me though by mentioning my website and my articles. Now I
CJ
don't
wrote
have to do it.
a lot of very nice articles on competition math and other subjects, and he has a very nice website too, which you should check out. So, yeah, thumbs up. Okay. You are more than free to go if you would like, CJ.
Thank you. Bye.